Hello scholars, welcome. So happy to continue our discussion. We're really looking at plate tectonics and how we got to this idea of the unifying model for how geological processes function. So to remind us, plate tectonic theory states that the surface of the Earth is covered by large, rigid blocks of rocks called tectonic plates. And where tectonic plates meet one another are tectonic boundaries. And it is at these tectonic boundaries that we have earthquakes and volcanoes. We have mountains that are building, oceans that are forming, old crust being consumed, and the driving mechanism of how continents move across the surface of the Earth. So today's lecture is looking at geophysical evidence. So this is out of the idea of continental drift and into the idea of plate tectonics. And how did we get there? So we will look at the continental drift hypothesis and how it transformed. And then we'll look at the lines of geophysical evidence that support the theory of plate tectonic drift. Okay, let's go. Quick review. Continental drift is a hypothesis proposed by Alfred Wegener, formally in his book in 1915, first in 1912, that he said the continents drift across the surface of the Earth. He had 4 lines of evidence: the puzzle piece fit, the shape of the continents, matching geologic units on opposite continents, past climates looking at coal and glaciers, and fossils, land fossils that were discovered on multiple continents across the world. So compelling evidence for this idea, but no mechanism. The mechanism wasn't discovered until after he died. The mechanism is the grounds for plate tectonic theory, the unifying theory, explaining the structure, how landforms are created, and how tectonic plates actually move. That's what we're doing today. So quick rundown. 1912, Wegener proposes continental drift. 1930, Wegener dies on his 4th expedition to Greenland. Sorry, buddy, he was never validated for his idea. In fact, he was laughed at by the geologic community. 1950s, so 1940s, World War II, lots of data collection. 1950s, these data are processed and begin to support Wegener's ideas. 1960s, we actually have evidence to provide the mechanism for plate tectonics and the development of the plate tectonic theory through to today, continuing, ongoing GPS, where we can actually measure the movement of the continents. So it's a rich history. It's a recent history, 1960s. So within the last 70 years, we finally have come up with a framework to answer the questions: how do mountains form? Why are the oceans where there are oceans? Why do we have earthquakes? Great questions. Now we know. So went a little bit like this. World War II was in the 1940s. Naval warfare was a thing. And part of that, the American military was collecting all kinds of sonar data, which basically was emitting sounds into the bottom of the ocean, recording the time for that sound to reflect off the bottom and come back. This gave an idea of what was down there. So having an understanding of the ocean bottom was a strategic advantage. Well, out of that, the data was declassified in the 50s. And all of those data were put together to create this majesty, this majestic map that was a huge innovation in cartography and in our understanding. Bruce Heason, Marie Tharp collaborated. Marie Tharp, as she's putting it together, recognizes the existence of this underwater mountain range in the middle of the Atlantic, the Mid-Atlantic Ridge. The Mid-Atlantic Ridge. We did not know that there was an underwater system of volcanoes. Now we know that it is one continuous feature, the longest largest geologic feature on Earth. 65,000 kilometers, about 40,000 miles of continuous underwater volcanoes where new Earth is being created as we speak. So this discovery was huge. There's underwater volcanoes, an underwater mountain range. This is helping usher in this new age of plate tectonics. Not only was there underwater volcanoes, but there was underwater trenches. So let's draw a little transect, the bathymetry, across the Atlantic Ocean. We could start from, say, New Jersey, coast, continental margin, comes down like this, and then there's an elevated profile with a little valley in the middle of it, goes down to the other side. And say we're going to go to Spain on the east side of the Atlantic, something like this, right? The general topography or bathymetry of an ocean basin. But in certain areas of the world, we also have what are called trenches, very deep areas of the ocean. So the 1950s helped us to understand what the shape of the ocean basins was like, where there were mid-ocean ridges, and where there were ocean trenches. Great. Having an understanding of the way that it looks was the next step forward, because when Alfred Wegener was around, no one knew what was at the bottom of the ocean. In fact, the very first time that we discovered the oceans weren't flat was during the voyage of the HMS Challenger that took on the systematic study of the oceans in the 1870s to collect scientific evidence for depth measurements. They threw some rope over the side of the ship. It went down and down and down in this area that is now called the Challenger Deep. Get the connection? HMS Challenger, Challenger Deep. But now, with the use of sonar technology, we could get this idea of how deep and where and the shape of the ocean basins. Okay, great. So the shape of the ocean basins is one of these lines of evidence that it is one of the modern geophysical lines of evidence, and I want to start creating a list over here that allowed us to fully develop modern plate tectonics. So shape of ocean basins. It seems so simple. Like, oh, the bottom of the oceans have a bathymetry or a topography or a shape to them. But it was a crucial step for us to understand how our Earth works, just to know what they look like. Harry Hess was in World War II. He was a captain, turned geophysicist, became a professor at Princeton, and he was learning some of this information about the shapes of ocean basins. And he was taking in this new information, the fact that there was a mid-ocean ridge system, the fact that there were volcanic trenches, and he developed the idea of seafloor spreading. So maybe I come back. I erased it too soon. So at the mid-ocean ridge discovered by Marie Tharp, Harry Hess said, well, if these are volcanoes, these volcanoes are erupting and creating new crust that's pushing in opposite directions outside of the mid-ocean ridge. And he called this seafloor spreading. Seafloor spreading occurs at mid-ocean ridges, and it creates new oceanic crust. What an idea. not only did he look at mid-ocean ridges, but he looked at these trenches and said, at oceanic trenches, we have a boundary where this oceanic crust is descending into the earth and is being consumed by heating up and becoming part of the mantle again. Hopefully you can see that I'm not too far over. Let's get this in here. Great. And being consumed. So seafloor spreading and subduction are processes by which plates move across. So we're getting more towards a mechanism. What's the mechanism for plate tectonics? Seafloor spreading and subduction. These are processes for how tectonic plates are going to move across the surface of the Earth. The mechanism is because of Earth's internal heat that's moving through the center of the Earth in convection patterns, convection cycles. So the crust is thin. I have another lecture, so I'm not going too deep into this. If you really want to see the mechanism, please see that one. But in the context of geophysical evidence, seafloor spreading and convection states that there are convection cycles that are driving seafloor spreading to occur. Hot magma comes up near the surface, it erupts as volcanoes, creates new crust. That crust pushes outward, it moves across the surface of the ocean, and eventually is recycled back into the Earth at a subduction zone. So, seafloor spreading, subduction, we have convection cycles from Earth's internal heat. Great, okay, we're building a case. So now we've got an understanding of the way the ocean floor looks. We have process, seafloor spreading and subduction. We have a mechanism, convection, that's moving heat, driving the processes of seafloor spreading and subduction. We're building a case. This is all adding on to Wegener's idea of continental drift, that the continents look like each other, right? Africa and South America fit together like puzzle pieces. Matching geologic units, past climates, and then also fossil evidence. This is great, but let's keep going with the modern evidence. So around the turn of the 20th century, the ability to put absolute dates on rocks through properties of the elements was created. It's called radiometric dating, or isotopic age dating of the various minerals. During the 40s and the 50s, cores were drilled into the crust, and these cores were pulled up and analyzed, and dates of the rocks were put on them. And what do we find? Here's South America, North America, Africa, the Mid-Atlantic Ridge. When we put radiometric age dates on the rocks at the bottom of the ocean, we see that the youngest rocks on either side of the underwater volcano range are youngest closest to the mid-ocean ridge. The further away you get, the older these rocks become. Because, let's see here, when this rock erupts, its age is 0. As new rocks come in and push it, it gets older. As it's pushed further over, it gets older. As it continues to travel, it gets older and older and older. So we have young at the mid-ocean ridge, old at the perimeter of ocean basins. Great, okay, so let's zoom way out. We have the idea of continental drift. We have a greater understanding of the shape of the ocean floors, which leads us to processes of seafloor spreading and subduction driven by the mechanism of convection cycles. We're really gaining evidence. Now we want to be able to say plate tectonics and continental drift are happening, but How do we know that? So we look to the age of seafloor sediments and the age of seafloor crust. I think that would be more accurate. The age of seafloor crust to prove these ideas that the surface of the earth is moving. Because I don't know about you, but I go outside, I ride my bike every day when I come to campus in order to study and learn and film these lectures. And underneath of my feet, this continent is not going anywhere. Hasn't moved on me once. But that's not how plate tectonics works. It moves in fits and starts. When an earthquake occurs, there's shaking, and that's when the movement of Earth's tectonic plates happens. But let's continue. Magnetism. So the center of the Earth is like a big magnet. Because early on in Earth's formation, when it was one big homogeneous ball of material, it differentiated, it stratified by density. The heavier materials to the center, the lighter materials to the exterior, and the iron, mostly iron, 95% iron, 5% nickel, sunk to the center of the Earth and created a giant magnet. That is how come, if you have a compass, it orients to Earth's magnetic field. This is amazing because Earth's magnetic field is so strong it fends off solar winds that otherwise would strip us of our atmosphere, but that's another conversation. So this magnetic field, it penetrates all the layers of the Earth to the outside of the Earth, and what happens is when new rock forms, the Earth's magnetic field is locked into those new rocks that are being created. There's an entire field called paleomagnetism. Paleo means old or ancient, where we're looking at the orientation of Earth's magnetic fields. And sometimes Earth's magnetic field is in a positive direction, meaning it goes one way. And then sometimes it flips and it goes the other way, in the opposite direction. And these magnetic reversals are actually recorded in the rocks. Here, this is a really cool animation showing reversed versus normal. The strips are a different color versus reversed versus normal. The strips are a different color. Using a magnetometer, this also occurred during World War II, the magnetic anomalies of the seafloor were mapped. And they pretty much align on opposite sides. There is a symmetry on opposite sides of the mid-ocean ridge that show positive and negative anomalies, which are interpreted to be regular and reversed polarity. So magnetic polarity, as recorded in the rocks, is another line of evidence that shows these rocks are being created at seafloor spreading centers, mid-ocean ridges, and they're moving across the surface of the Earth. Whoa, let that one sink in. But it gets even bigger than that. Oh my gosh, really? Okay, so lava flows over the surface of the Earth, and lava is hot. Watch out for the hot lava. But when it cools, there's little tiny magnets in it. And those magnets, they're grains of magnetite that have iron that align to Earth's magnetic field, point to the current location. So let's do this. It's kind of like this. So if these are together and Earth's magnetic field is like this, why don't I do it like this on this one? Okay, I'm going to hold it on to Africa and say, when the lava erupted and Pangea formed, Earth's magnetic field is pointing up to the top of Earth up here. And then these two continents drifted away, just because I only have so many hands, to this location. Well, Earth's magnetic field is up here. But notice my pen is pointing in a different direction. So at the time of formation, those grains locked in the location of the magnetic field at that time, and then it moved since then. This is called polar wander. And if we take the locations for where the successive layers of lava flows are pointing to, and then you take two different curves on opposite continents in North America and Asia, and you put them back together, you move the continents. Essentially, you take in the reverse, right? So we're taking it like this. We're saying, here's this magnetic field. Earth's current magnetic field is up here, but these rocks are pointing this way, so let's move them back like so. And you do the same thing over there. Then you can recreate. This is how there's really cool animations on paleogeography. And it shows the continents moving across the surface of the Earth and coming together to form supercontinents and splitting up again. And I was always curious as a student, how do they do that? How the heck, how could you possibly know how the continents have moved over billions of years? And the answer is, well, the rocks tell us. The rocks tell us because at the time of their formation, they are locking in Earth's magnetic field, the paleomagnetism, and we can recreate their location through Earth's history. This is actually polar wander, talking and writing at the same time. Through Earth's history to recreate the paleogeography, or the location of the continents in Earth's history, so we have an idea of how these landscapes changed through time. Whoa. Now we have seismometers that record seismic waves. Every time an earthquake erupts, anytime there's tectonic activity. So an earthquake occurs when there's movement along a plate tectonic boundary, a shift along, or a fault, right? When there's a shift along a fault, there's movement, releases seismic waves. Well, we can trace out the location of the epicenter of seismic waves, and they carve out, they basically give us a map of all the plate tectonic boundaries. If you look at a map of the world's earthquakes that we've measured for over 100 years, it pretty much perfectly aligns with the world's plate tectonic boundaries because these earthquakes are happening at the interaction where two plates meet. Awesome. Okay, so let's keep going, right? We've got age of seafloor, magnetic polarity, polar wander. We've got some evidence to support these ideas. Now we need to put it all together. J. Tuzo Wilson proposed the Wilson cycle that said continents will begin to separate and form a continental rift in the center. That continental rift will continue to open until new ocean crust starts to fill in the gap, creating two new plates. Those plates will move apart from each other. At some point, one of those plates will become a subduction zone, and crust will be consumed, and the ocean basin that had once opened will now start to close in on itself. And this is a cycle that is repeated. This is the explanation for the development of supercontinents, our most recent one being Pangaea, which we lost. Oh, I think that was in my last lecture. Being Pangaea. But supercontinents are happening on a cycle that occurs every 500 million to billion years. There's been evidence of at least 4 supercontinents in Earth's history. And right now the continents are pretty spread out, but at some point they are most likely going to come back together again and form another supercontinent. So we put all of this together. Wegener's idea of continental drift, new, modern, geophysical evidence, and synthesize it into the theory of plate tectonics, which is awesome. And it states that the surface of the Earth is covered by large, rigid tectonic plates. And these plates actually move around relative to one another on the surface of the Earth. And where they meet, they form tectonic boundaries. These active boundaries produce earthquakes. They build mountains. They create oceans. They close ocean basins. Landforms and geologic processes on the surface of the Earth make sense through the lens of plate tectonics. So this is our best current understanding for how geology works. It is the theory of plate tectonics. It is the unifying theory of modern geology, a single model of Earth dynamics, and it helps us understand so much of what we see on this Earth. It had a long history, but here we are, and now we can utilize this theory in order to understand more complex processes about how our Earth works. So, thank you so much. This is a really big topic. It's really important. And as we continue in our studies of geology, of Earth's surface processes, this is the theory that helps us to understand, for it all to make sense. Great. I'll see you again. I'll see you in the next one.